there! This video lab report is a presentation on Newton's first, second, and third laws of motion. My name is Aubrey Rollins, and this is for Physics 114. Newton detailed in his work Principia 3 laws of motion. This series of work was first published July 5, 1687. To begin, Newton's first law, sometimes referred to as the law of inertia, states an object at rest or in motion will remain in that state unless acted upon by another force unbalancing the system. In a system where we have an object such as a refrigerator resting on the ground, this object will remain at rest. If you act on that refrigerator by pushing it and it moves, you have added a force unbalancing the system. Likewise, if you have a refrigerator sliding on a frictionless surface after receiving a push, the refrigerator will continue to move in a straight line and at a constant speed until acted upon by another force. Both at rest or in constant uniform motion, the system has a zero total net force. We ran PHYS simulations to show this in a perfect world. Here you can see screen captures from all experiments. In this first picture here, we have an object at rest with a zero speed, zero acceleration, zero applied force. Here we have an applied force, a speed, and acceleration that happens while the pushing force is happening. After letting go, and here on a frictionless surface, we can see applied force is now zero again, acceleration is now zero again, but our speed is a constant 29.8 miles per hour. Uniform motion diagram brought back from first chapter here, and a free body diagram here showing a zero net force. Top we have our normal reaction force. Down here we have our gravitational weight force, which cancel each other out. And here in the center is our object of interest, in this case a fridge. In reality, we use this first law every day to predict the motion of objects in our world. We have a refrigerator stationary in the house. When we come home, we can predict it will still be there. If we put something somewhere, we can trust it will remain there. If we want to change that, we have to apply force. Which brings us to our second law. To start, common forces are gravitational weight force, which is weight equals mass times gravity. Weight is the force we feel from our mass and gravity acting upon. Normal reaction force is the opposite reaction to weight force. It is the ground that provides a force to combat the weight force. Friction force is between two surfaces that contacts and slides against each other. The surfaces of the two objects in contact acting against each other is what causes friction. Tension is the pulling force on an object via a string, a rope, or chain, etc. And that is mass times gravity plus or minus mass times acceleration. Push-pull, or general force, is a force you can directly put on an object to move in the direction that force acting upon the object is moving. And our second law, Newton, which is for force, equals mass times acceleration. Newton's second law. This law, Newton offers an equation. One talked about just previously Force equals an object's mass times its acceleration. This explains that an object which experiences acceleration must have a net force, and vice versa. Mass and force and acceleration and force are directly proportional. This means a greater force yields a greater acceleration. A greater mass yields a greater force. A lighter mass yields less force, and a lesser force yields less acceleration. Mass and acceleration, however, are inversely proportional. A greater mass yields a lower acceleration. A lighter mass yields a greater acceleration. Net force and acceleration are both vectors, meaning they have a calculable magnitude and show direction. Net force and acceleration will be equal and face the same direction. Intuitively, we understand this. It is more difficult, i.e., more force is required to push a large stone statue with a large mass than it is to move a toy figurine with a smaller mass. And once those objects get moving, a heavier object will accelerate slower than an object that is lighter. Here we have screen captures from our PHYS simulation experiments. Showing that something that weighs more requires more force than something that weighs less requires much less force. Now we're comparing different objects. Let's move on to Newton's third law. Newton's third law says that for every action there is an opposite and equal reaction. This system is comprised of two objects, also known as a Newtonian pair. The system wholly considers the relationship between the two objects in contact with each other. Whatever force one is exerting on the other will be returned in a reaction of equal but opposite force. These cancel each other out. We have to look at the pair of objects together in order to show these forces. If we isolate one of the objects, the other becomes either isolated. Whatever pair isolates in the of two bodies on magnitude and opposite direction. Two people. These as Newtonian pairs that both in the same positive sign and negative direction. Goes for a person on a wall. If you take and the person as the wall are opposite direction. We have a diagram. This impact the blue equals the total. In conclusion, laws of the United